put Brian, can you hit the bottom right light switch for me? Thank you. All right. So, carbon is the single most important atom in biology. As a reminder, its mass number is 12. Atomic number is 6. Okay. Often referred to as the backbone of life, or the foundation of organic chemistry. So, a carbon atom Sophia, if its atomic number is 6, what does that mean? Six electrons and 6 protons, right? So if I'm filling out my electron diagram, remember this first shell can only hold 2 electrons, so we've got 1, 2, which means we have a total of how many valence electrons, Angel, in the outermost shell? 4, right? We have 4. Why that's important is because this gives carbon the ability to form 4 covalent bonds, right? Because if you remember the octet rule, it wants to fill that outer shell with 8 electrons. So it can form 4 covalent bonds, which will give it 8 electrons in total. This means that it has great flexibility. It can form huge molecules. So carbon can form huge molecules or macromolecules that you'll learn about. So for example, let's take a look at this. So this is a molecule called methane, or CH4. Remember chemical formulas, they indicate how many of each atom. There's 1 carbon here and 4 hydrogens. Okay. We have 4 covalent bonds. Jezre, between carbon and hydrogen, which has the higher electronegativity? Carbon, right? So carbon, remember this scale has the higher electronegativity just a little bit. So although there's a partial negative charge here, technically, the molecule is not polar because what's on the outside? It's on a hydration shell, but we have all hydrogens, which will be all positively charged. So you're not going to see like water molecules where you have part of the molecule negative and part of it positive. That gets into the structure of the molecule, but for our intents and purposes, this is not a polar molecule. All right. We've got 4 covalent bonds. They're single covalent bonds. Okay. Carbon can also form double covalent bonds. Most commonly, this is carbon dioxide. But still notice that a total of 4 bonds have been formed on carbon. Okay. All right. If you made it a little bit more complicated, I can throw in 4 carbons. And notice that the internal carbons, they only have 2 hydrogens, right? But every carbon will have a total of 4 bonds connected to it. Chemical formula here is C4, and then I've got 10 hydrogens. Now, organic chemists and biologists, to make things simple, they draw line diagrams instead of drawing out all of the carbons, all the hydrogens. So this molecule actually can look like this. That's the same thing. Yeah. Yeah. So whenever you see something like this, a corner or an end that's not labeled, that just is a carbon. Okay? And then you notice they don't even draw the hydrogens attached at the ends or in the middle, right? But we'd imagine there are 2 hydrogens here. It's just assumed that that is the case. Okay? But every carbon has to have 4 bonds, so whatever is not taken up has to be filled with a hydrogen. Okay. C4H10 can also look like this, right? And if you count up all the hydrogens, you'll still have 10 hydrogens and 4 carbons. We call these 2 isomers. That just means that they have the same chemical formula, but different structure. All right, one's linear, one's branched in this case. If you were to draw the funky little line diagram, looks like that. I did not enjoy organic chemistry in college. All of these lines going all over the place. But just so you were aware, that's how you read these. This is the same molecule. All right. So last thing, something they got really excited about when I was in organic chemistry was they told me about a molecule that actually exists. And it's my favorite molecule, if that's a thing. My spirit molecule. That's a thing. But you'll get why. So here's a more complex molecule. All right. That is a molecule that actually exists. A couple things you want to point out here. So, remember all the corners and all the ends are carbon atoms. We've got a double covalent bond between these carbon atoms. We've got a double covalent bond between this carbon and the oxygen. Okay. The name of this molecule, I'm not even kidding you, is penguinone. It looks like a penguin with a little dark belly, or the dark sides and the white belly. That's called penguinone. It's literally a substance that exists. So, your job right now is I want you to determine the chemical formula. Okay, so go ahead and fill in the subscripts. How many carbons, how many hydrogens, and how many oxygens are in penguinone? More with your neighbor. Yeah, that's oxygen. Right.
Wait, but there's those double bonds, yeah. I swear I'm counting 10. I swear I'm counting 10. Okay, so look, each end, so 1, 2, 3, 4, 5, 6, 7, 8. Wait, I thought it was like the ends of like this. I thought because like this, I thought this meant double bond. Did he just say that?
This is a double bond. That's a double bond. The double covalent bond is between the carbon and the oxygen. And then you have the other two carbons here.
So like you know those two lines at the end,
Which ones?
like the ones
these two?
like no like the ones up like above it, yeah, the parallel.
Yeah,
Are those double bonds?
that's a double covalent bond. Yeah, you got it.
This these are double bonds.
Okay, that makes a lot of sense.
Oh wait.
Oh, wait. Wait. I think it's not. Isn't that 2, 3, 4? Oh, so yeah. So 1, 2, 3, 4, 5, 6, 7.
I think that's coordinates.
No, also in the end.
Oh, I thought it was
Like, see right here. See in the end that it's not labeled.
oh, that's so.
Does that mean that this is also, or is this just one carbon? Okay, cool.
Sophie, did you table get it? Did you table get it?
We got something, but I don't think why.
Here you have one.
All right, let's bring it back together. In 3, 2, and 1. All right, Wenji, how many carbons we got? Got 10. Great. So let's double check. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Great. We've got 10 carbons. When you do these, it's easiest to do hydrogens last. So in this case, Angel, how many oxygens we got in this molecule? 1. Just 1 at the top here. Now let's count the hydrogens. Let's go to William. How many hydrogens we got? 20? Okay. So a little high. Does anybody have a different answer? Let's go right here, Henry.
21.
21. Well, still too high. Angel? 14. So let's double check. So we start with each carbon. Does this carbon have 4 bonds already?
No.
Yes. So we got a double and 2 singles. That's 4. So there's no hydrogens. Here, we've got a single and a double. That means there's 1 remaining. Okay. Here, we've got 2, 3, and 4. So there's no hydrogens there. That's a full carbon. Here we have 4. Here, though, we only have 1, so we've got 3 hydrogens. Same thing here. Same thing here. Same thing here. All right, this is a symmetrical molecule, so it'll be the same thing on the other side. So we just have 1 little hydrogen there, and that's it. So we got 1, 2, added to 12 for a total of 14. So our chemical formula, C10H14O. Usually you don't write the 1. Penguinone. All right. Question? Yeah. So how many covalent bonds can a carbon form? 4. Bless you. Well, bless you. So we went 1 by 1. And here, for example, Alexia, there's only 1 covalent bond between a carbon and a carbon, right? So that leaves 4 available.
I don't know that one.
Wasn't asking you. There were 3 remaining spots in the outermost shell of the carbon. So they formed 3 bonds with hydrogens.
Oh, to fill in the...
Yeah. Here, though, because there's only 3, right? There's 1, 2, 3 covalent bonds. 1's remaining. Hydrogen. Everybody got it? You counted the lines?
Yeah.
That's maybe just a coincidence. I would go through and actually count them. Penguinone is just an exceptional molecule, so that's probably why that works out. All right. Let's